Hey everybody, this is Mr. Piercy, and what we're going to be looking at in this lesson is what happens to a right triangle when you draw an altitude from the right angle. Now, what happens really is that the triangles wind up becoming similar to each other. Now, in a right triangle, obviously, we have two sides that are already perpendicular to each other that we refer to as the legs of the right triangle. Because they do fit the definition of an altitude, meaning it must come from a vertex going to the side opposite of it to form a right angle, we do have two altitudes already built into the triangle. Oftentimes we'll think of those as the base and or the height of the triangle whenever we have to figure out the area of a triangle. However, now what we're looking at is the third altitude as it's drawn from the vertex where the right angle is. And what it winds up doing is it divides the triangle into three separate triangles. We have a big triangle, a medium triangle, and a small triangle, and they all wind up being similar to each other. So looking at that, one of the things that we want to be able to do is, can you identify them? Now, the strategy that we're seeing here is something that I strongly recommend that you try to do if you're having a hard time identifying individual parts of the triangles as they're kind of grouped together. So what you start off with is kind of a triangle like this, where segment GJ is the altitude of the triangle from point G. And so what it's doing is it's creating three separate right triangles in the figure, a big one, a medium one, and a small one. Well, one of the things that I know that students have a hard time with is that when the triangle is all kind of together the way it is presented, that sometimes we have a hard time seeing, well, what sides actually correspond to another side. So the way that we kind of approach the problem is what we see right here, is we just draw three separate triangles in the same orientation. And it allows us to identify parts that kind of go together, whether it's an angle or a segment that we're looking for. We always draw them in the same orientation, like what we see here. And by separating them into three separate triangles, we can focus on which part goes where, what segment length do we know, and therefore it will allow us to identify triangles or sides that are corresponding to each other that allow us to write and solve proportions. So the way that we're going to kind of fill these in is just with the names of the triangles, and they didn't have to be in this particular order, but that's what they were doing, or that's how I decided to write them out. So at this point here, go ahead and pause the video and try to identify the three similar triangles. And if you need to, which especially for the first time or two, you might want to definitely try, separate the triangles into their three separate parts so that way you can identify what the triangles go to, or how we would name the similar triangles. But go ahead and pause the video, do checkpoint question 1, and when you're done, hit play again. All right, so hopefully we have our triangles identified correctly. And what we're looking at here in this particular triangle, there we go, oops, didn't mean to do that. The way that I named these particular triangles is triangle NLM, LPM, and NPL. And the way that I'm doing that is, what I'm really going to do is I'm going to just start by drawing some triangles in the same orientation. And I'm going to take the first one, NLM, and say, okay, well, there's that one. Now, the one that I'm really kind of looking at each time to start me off with is I'm going to be looking at where's the right angle located. Okay, so for my other two figures, I want to know where's the right angle going to be located. So on my medium-sized triangle, my right angle is point P. Now, the long leg of the right triangle goes from P to M, and then the short leg goes from P to L. And then I'm going to look the same way on the right triangle, the small figure. The right angle has point P, and the long leg goes to point L, and then the short leg goes to point N. And then if we needed to, we could actually, plug in the values that are presented in the figure, so that way we could easily identify what sides correspond to each other to set up and solve a proportion. So here's an example of how we're actually going to be using the similar triangles to set up and solve a proportion. Now again, up at the top where it starts with the problem itself, Stadium A, that's all you're giving, or that's what you would typically be given in a problem. So for the time being, just kind of ignore that the stuff is there. Well, here we have our altitude drawn in from the right angle. Well, because it's the altitude drawn from the right angle of a right triangle to the hypotenuse, what it's doing is creating three separate triangles. And the question is asking us, well, how long is that pipe going to be? So the way that we're going to kind of take a look at it now is, again, well, I'm not sure which parts go with which triangles, so I'm going to separate it into three separate triangles and label each side so that way I can see, well, what sides actually correspond to something else. And we can see in the big triangle, we actually know all three sides. So we could look at the big triangle and find anything that was missing in either of the two smaller triangles. Well, in this case, we're looking for segment BD. So looking at it here, I could probably say the hypotenuse of the big triangle with the hypotenuse of the medium triangle, and then I could look at the short leg of the big triangle and the short leg of the medium triangle. We could look at it like that. But we could also say, well, what about the hypotenuse here and the hypotenuse here with the long leg here and the long leg here? You could absolutely set it up either way. So here, naming the triangles, this is how I decided to name them. And now the way I color coded the values of the triangle, we could set up a proportion either way, but based on the fact that the notes are kind of giving us segment BD and segment AC, in where they are, we're going to go ahead and just kind of plug in the values of their corresponding sides. So I'm going to say BD to AB is equal to BC over AC. And then just substituting the values, we're going to solve for x. Okay, cross multiply, and we're going to get 10 radical 13 is equal to times x is equal to 300. And then we will just divide 600 by 10 radical 13, and we will get about 16.6 feet for our answer. Now real quick, let me go ahead and just kind of demonstrate what's happening here at our work here. I don't want yellow, I wanted red. But hopefully we can see the yellow anyway. But what we're saying here is we're going to say, and please make sure you copy this down into your notes. If we say 10 radical 13 times x to be equal to 600, what's happening to get our our exact answer, what we're going to wind up doing is something, we're going to have to do something called rationalize a fraction. So when we multiply x by a radical number, we get rid of it by dividing, which gives me 600 over 10 radical 13. And that was a bad 3 even for my handwriting. 13. One of these days I'll get it right. Radical 13, there we go. Now if you type the square root of 13 on your calculator to get a decimal value, its decimal equivalent, it's going to give you a what we would classify in math as an irrational number, meaning it is a non-terminating, meaning it never stops, and non-repeating, meaning it's not like 0.33333 or 1111111. It's not. It's a non-repeating, non-terminating decimal number. So the square root of 13 is considered irrational. And because it is irrational, it cannot remain in the denominator of a fraction, because essentially what you're trying to say is I'm going to divide with this number that never stops. So what we do is we rationalize it. And the way that we do it is I'm going to take the radical value and I'm going to multiply it to the numerator and the denominator in order to maintain the same ratio. So if I do something to the top, I have to do the same thing to the bottom and vice versa. Now in the numerator, 600 times the square root of 13, we leave it in simplified radical form. And I forgot to put, this is 130 here. And so here we're going to say 10 times radical 13 times radical 13. Well, square root of 13 times square root of 13 is just 13. So here we get the 600 radical 13 over 130, and the, oh, no, I didn't need that zero there. And 600 over 130 simplifies to be the 60 over 13 with the radical 13 in the numerator. Now we're going to be seeing that a little bit later on, the rationalizing part of the math, when we start working with special right triangles. So since we have math with the radical here, I want to go ahead and introduce you to the vocabulary. So go ahead and now that we're here, go ahead and find the missing value, find the value of x, and when you're ready, go ahead and hit play again and compare your answer and see what I got. Okay, so in this case, no radical values for the stuff that was given to us. 6, 8, 10 is a Pythagorean triple. It's just a multiple of the 3, 4, 5 triangle. And one of the things that I'm going to do is, first thing I want to do whenever I work a problem out like this, I'm going to take the time to just, write out the 3 different triangles. And that is one of the things I ask you to do, is identify the 3 similar triangles. So here we go. So now that I've done that and I've labeled all of their corresponding parts together, the way that I chose to set up and solve my ratio is I said segment FD over DG is equal to DE over GE, and substituted their particular values and solved for X to be 4.8 units long, whatever the unit of measure is. So here, basically the same thing, but now we're getting into the geometric mean. Okay, now the geometric mean, if you remember from our previous lessons on similarity, is basically we're going to have the geometric mean is equal to some segment times another segment, whatever they are happen to be. Basically, in this case, the geometric mean is really what we think of when we're trying to find the height. Now, I want you to understand that the work that they're kind of setting up here is not the only way that you could do the problem. Again, if you separate the triangle into 3 separate triangles, you can pretty easily identify more than one way to set up and solve the problem. So if we say F, E, D, and then I'm going to say G here for the medium one. So this is D and E here, and then we have G here going to E for the long leg and F for the short leg. Okay, well, let's go ahead and plug in our values. We know that the hypotenuse of the big triangle, FD, is 15, and that its short leg is the variable y. And then we know that FE here is y, and that FG is 4. So looking at the values here, and if we really wanted to, we could figure out that for segment GD, we could say that that's 11, but we don't have anything else really to go with it. So if I wanted to know what GE is, that's when I would really kind of start thinking about using what we typically think of as the geometric mean. Okay, but looking at the values that we have here, well, we can see we have the short leg of the big triangle and the short leg of the little triangle with the hypotenuse of either of those triangles. Now, the reason why they're specifically saying it's the geometric mean here is because you can see when you cross multiply, we're going to say y times y, which is going to give you y squared. So when I take the square root of those two sides, square root of y is square root of y squared is y, and the square root of 60 is going to simplify to be 2 radical 15. And you can see here off to the side, I'm giving you the discrete steps. What we're looking at here, what I'm doing is what I'm looking at here is what's the biggest perfect square factor of the number 60? Well, 60 has a bunch of different factors, like 2 and 30 are factors, and 10 and 6 are factors, but none of those values are a perfect square number. The only perfect square number that is a factor of 60 is the number 4. So its other factor with 4 would be 15. So the square root of 4 is what produces the 2 as the whole value. And since the square root of 15 cannot be simplified as radical value, it stays in radical form. So here we're looking at the two ways that we can write geometric mean. The first one that we see up at the top, that one is something that we've seen before, specifically with geometric mean, not necessarily related with triangles, but at the time I mentioned that, well, that's what we're really going to be using geometric mean for, is when it comes to the altitude of a right triangle. But because the altitude where the geometric mean is found kind of separates triangles into three separate triangles, well, what we're seeing here is ways that we can kind of compare the ratios so that we can have a proportion. So if you look, we're looking at AB over CB. Well, AB and CB are the hypotenuse and short leg of the overall big triangle. So then I'm going to look at a hypotenuse and a short leg of another triangle. So in this case, we would say CB over DB. And same thing with AC and AB and AC. Well, AB and AC is the hypotenuse and the long leg of the big triangle. So I can say the hypotenuse and the long leg of the medium triangle as well. And this is kind of how we're going to be looking at it. It's not always going to be in a problem format like this, but we have a person that's trying to approximate the height of the column of a highway overpass or something. And what we're doing is we know that his eyes are 5 feet above the ground, and he is standing 6.9 feet away from the column. So he is essentially creating some right triangles here that use the geometric mean and separating the triangle into its corresponding parts if you needed to. But we would say here 6.9, this is the short leg of a triangle, and we know the long leg of a triangle. And we also know that 6.9 is a long leg of the triangle, and we know a short leg here. So we can kind of see we have two long legs and two short legs from similar triangles that we're going to be looking at to solve for the missing value. Now, again, the reason why it's really going to be a geometric mean is because we're taking two things and we're multiplying them together. In this case, 6.9 is going to be the value it's going to be used twice. So even though we're not having to necessarily take the square root of something, it's because we are multiplying those two values that are the same, 6.9 and 6.9. That's how we're getting our particular value. So in this case, when I solve for x, I get about 9.5 feet. And when I add it to the 5 feet of the person's height, that overall gives us about 14.5 feet overall for the highway overpass. So here is your last two examples. Find the missing value here. If you need to, go ahead and separate the three triangles into their individual triangles, or separate the figure into three individual triangles so you can see what parts go together. And question number 4 refers back to the highway overpass diagram that we were looking at. So go ahead and pause the video, answer these two questions, and see what you come up with. All right. So looking at the triangle here in problem number 3, find the value of y. Well, here y is a hypotenuse of the short leg, or of the small triangle, and I know the short leg of the small triangle as well. Now, next thing I'm going to kind of look at is I know that y is also the short leg of the big triangle, and here the 24 is a hypotenuse. So I can recognize I can have the ratios of a hypotenuse to a short leg and a hypotenuse to a short leg for my proportions, or a short leg to a hypotenuse, however you wanted to do it. So I'm just going to say y over 24 is equal to 9 over y. Multiplying, cross multiplying gives us our y squared, which is where we're talking about geometric mean. We have to take the square root of the product of two numbers. So simplifying the value, I get 6 radical 6 as my uh, value for y. Now in this one here, we're going to look at the diagram. Instead, well, Larry's eyes are not 5 feet, they're actually 4.5 feet. So we already kind of know that the value that we found before, the 9.522, we can kind of use that again, but now Larry has to stand a little bit closer to the column, and that's the value that we're trying to find. And this is very typical of what we think of as the product of, or as the geometric mean. So for instance, if I said this is A, and this is B, and this is C, typically we just think of it as the square root of AB times BC. And that's basically what I did. I took the same value that we had before, multiplied it by 4.5, and took the square root of that product, and got about 6.5 feet. And that's how far away he is. So this is pretty much going to wrap it up here for our similar triangles. Again, keep in mind, if the altitude of a right triangle is drawn from the right angle to the hypotenuse, it divides the triangle into 3 similar triangles, which we can therefore set up and solve proportions with. And a geometric mean is just, it's included because if we're using the same value twice, ultimately we're going to square something, and we have to take the square root at some point. But that's pretty much it for similar triangles. You just need to be able to identify what are the corresponding parts, and then you should be pretty okay. But if you have any questions about anything, again, by all means, let me know what they are. And until next time, ladies and gentlemen, thanks for watching, and take care.